Good morning, everybody. Good morning. So we're starting to get the building cooled off a little bit, only because the temperature outside isn't so bad.
And every door is possible.
Every door is open. Yeah, so if you want to steal anything out of the storage room, now's your chance.
There's not much to steal.
There really isn't. All right, so straight out of the gate here, I've got to show you a lot of scary stuff. Okay? I'm going to show you some scary stuff, and I'm going to tell you not to worry about it. Okay? The reason, so what I want to do is I want to use Lorentz transforms as I want to do this very specific Lorentz transform with you that is useful. Okay? I'm not saying that Lorentz transforms aren't useful, it's just that there's a formalism to relativity that is helpful for you to kind of know that exists, and then we'll very quickly backpedal away from that formalism to be able to apply what's going on, right? So this is very useful for the theories. If you ever sit down, maybe watch a YouTube video, PBS Spacetime does this all the time, they use the formalism of relativity, and so they use this kind of language. And so I want to just expose you to it so that in the greater context, if you run across anything about relativity, general relativity, anything, you'll be somewhat familiar with what's going on. By formalism, what I mean is like the symbology and the language and the way we go about talking about things in relativity. I've been referencing these ideas without ever giving them their actual symbols and things like that. So let me just briefly try to explain. All of our problems up to this point have involved two frames of reference. Okay? Something moving relative to something else. And I've asked you to try to put yourself into the frame of reference of, say, the astronaut. And you've struggled with this idea that the astronaut would say that they're not moving and the rest of the universe is. It doesn't make sense in your brain because, unfortunately, you grew up on a planet with gravity and blah, 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 right? Okay? So being able to formalize mathematically, like in symbols, what those frame of references are, what they represent, we often do that by saying, okay, a frame of reference is has a coordinate system. And we can refer to those frames as capital S. So you have S for one object and S prime for the other object. So like the Earth could be in the S frame, and then the astronaut could be in the S prime frame. And if this were a physics class, if I was teaching a bunch of physics majors, I would start out of the gate by using all of this terminology, just to get them familiar and used to using it. Which a lot of you are engineers, you're not going to be doing any relativistic mechanics for a while. Come on, engineers, hurry up. And so the utility here is a little bit less. But I want to show it to you so that you can understand what we're about to do for a very application-heavy part of Lorentz transform. You can also see here that a lot of times the relative speed between frames is given as v, and then if there's any other speeds, like a particle moving within a frame, they'll not use v for that, they'll use u as a symbol. So if you ever see u's cropping up, like it's in your book or wherever, it's a speed measured by some frame of reference. So u would be measured in the S frame. U prime would be measured in the S prime frame. But v is the speed that each frame sees the other moving at. Now these pictures can get pretty complicated. Like here's something from a different book, right? And you look at it, you kind of get visually overwhelmed straight out of the gate. But realize, look, we got S prime, right? And if we've got distances in the primed frame, we'll put primes on it. It's a distance. And so what the Lorentz transform is, it's a way, it's basically Google Translate between frames of reference. If one frame of reference says an event happens there, then a different frame of reference has a different origin, doesn't it? And it's going to have a different set of coordinates for that exact same event. What the Lorentz transform allows you to do is go back and forth between the frames of reference. Like One frame of reference says it was at -3, 1, 0 for its coordinates. What does the other frame say? Now, because it's relativity, it isn't only about position. It's about time as well. In relativity, you can't separate space and time. It is one thing. Space affects time, time affects space, back and forwards, and you've seen that already with time dilation and length contraction. So in the Lorentz transform, as they're shown sort of on this freeze frame from a video we're about to watch, what do you know about everything that's on the left, just based on what I've taught you just now? All the symbols on the left have what on them? Prime. So we're talking about what is the x position in the primed frame of reference. Like one of the frame of reference is labeled as prime. The position that this person in the primed frame of reference, maybe the astronaut, if we knew the position in the non-prime, right, the Earth frame of reference, let's say, we know x, we can find x prime, but what do we need? Notice, what do we need? Time. This is the weird part. The Lorentz transform is not necessarily intuitive. But for frames of reference that are moving relative to each other, not only do we need to know the position in one frame, we also need to know at what time in that frame it took place so that we can make the proper, pun intended, translation. And of course, gamma is floating around in there, right? Because you expect. Now notice, x is different and t is different. T depends not only on the time, but also the position. Do you see it? Okay, it's just lurking in there. So one thing that the Lorentz transform teaches us, without actually me having to teach you how to use it, one thing that it teaches us is that time and space are all interwoven. We tend to teach you in classical physics that time and space, like they're separate and doesn't matter, right? T is the same for both x and y, and we're done. We can just move on with our lives. It's a great simplification. We don't come out of the great, day one physics 4A. Here's the Lorentz transformation, right? But space and time are definitely linked together. Now, what's happening with y and z? It's straight over, right? Remember I told you that length contraction, the contraction's only in the direction of motion, right? So in this particular Lorentz transform, the relative motion is along the x-axis, okay? And you always rotate your coordinates so it's always one-dimensional anyway, because doing 2 dimensions and 3 dimensions is dull. All right, so with all that being said, I'm going to teach you a specific application of the Lorentz transform called velocity addition. But before I do that, I want to show you this video that is going to give you a visual interpretation of the Lorentz transform. The Lorentz transform is mathematics, okay? But the video is going to give you an animation of what the transform is doing in the context of several of the video clips I've already showed you. It's a little bit long. It's like 4 or 5 minutes.
The fundamental concepts of space and time have become intertwined. The essence of the idea can be understood by visualizing time as if it were another dimension. Albert, standing still in space, flows through time. So that a vertical line represents a fixed point, x equals 0. In his reference frame at different times. While a horizontal cross-section represents simultaneous times in different places. On the other hand, someone in motion, Galileo for example, traces an oblique path. So while what Albert thinks of as a fixed point makes a vertical line, Galileo's idea of nothing happening appears as a tilted line at x prime equals 0, or anywhere else in his frame. But of course, if Galileo had drawn the picture, His line for standing still would be vertical.
That's the
And
transform.
Albert's would be tilted backward. The same idea can be used to show the relativity of time. When Henry and Albert observe the same expanding light sphere, it reaches their detectors at definite points in time and space. These are called events. Meanwhile, the light itself traces out a cone. To Albert, events on the horizontal cross-section are simultaneous. For him, one of Henry's detectors flashes first. Then both of his own flash simultaneously. And finally, Henry's other detector flashes. So he thinks these two events are simultaneous. But Henry thinks these two events are simultaneous. So not only are Henry's lines of constant position tilted, but so are his lines of simultaneous time. For Henry, simultaneous events take place everywhere on a tilted cross-section. So he thinks one of Albert's signals goes first, then both of his, then Albert's other signal. Of course, if Henry were drawing the picture, he would draw his lines of constant place and constant time perpendicular to each other. Amazingly, that wouldn't change the light cone at all. This way of looking at things is called a space-time diagram, and many of the strange effects of relativity can be visualized this way. For example, Albert thinks that Henry's ruler isn't quite a meter long, while Henry, seeing Albert speed by, thinks Albert's ruler is short. On the space-time diagram, Albert measures lengths on his space axis, where Henry's ruler is short. But on Henry's axis, the situation is reversed, and Albert's ruler is short. And what about the mystery of the clocks? How can each think the other's clock is slow? On the space-time diagram, just follow the bouncing light beams. On Albert's time axis, Henry's ticks are farther apart than his own. But on Henry's time axis, Albert's ticks are farther apart, no matter how he looks at it.
That rotation that they're doing there, right, that transform of the axes is a visual analog for what the mathematics of the Lorentz transform allows you to do, right? So I wanted you to just kind of see that in concept and then take you through a very practical application of the Lorentz transform, which is called velocity addition. So this comes back to Ratch and Jose and Abel, right? And their car, right? We started off relativity with this idea, right? That different observers in different frames of reference would measure different speeds for, say, a thrown baseball, right? Okay? And we were able to correct for the relative speed between the frames of reference and understand that, Jose standing there would measure the ball going faster, Abel would see it going slower, but they could reconcile their differences, right? Well, that's what we're going to do now, only we're going to do it relativistically, right? With all of the length contraction and time dilation involved with events taking place, we want to ask the question, what happens when two objects are moving and we want to calculate the relative speed that they see between them? In this type of problem, there are always three actors, okay? There's usually one spaceship, another spaceship or actor, right, okay, with observers in whatever frames they're in. And then there's some third person, okay, standing on a planet or maybe a different spaceship or something. There's always like a central observer that's saying that, well, the first spaceship is going at such and such a speed, and the second spaceship is going at such and such a speed, right? Maybe one spaceship is going, I don't know, 0.8 times the speed of light, and this one is going 0.9 times the speed of light. Both of those numbers are given by the person on the planet, right? The question we want to answer is, how fast would spaceship 1 see spaceship 2 approaching? And vice versa. The relative speed will be the same regardless, right? So if we step out of relativity for just a second and we say that you're driving 50 miles an hour north on Highway 41 and somebody else is coming 60 miles an hour south on 41, how fast is your relative, how fast are you approaching each other?
110.
At 110 miles an hour. How'd you do that?
Because if you're standing still,
Okay.
their speed. Yeah.
You did vector addition is what you did, okay? Positive 50 minus a minus 60 gives you 110. But if you're going 50 and somebody else is going 60 and they're in front of you, now how fast is your relative velocity? Negative 10. You're falling behind, right? So that's what we are trying to do, but folding in time dilation and length contraction. When we insist that the speed of light is the same for all observers, and you saw the light cone in those transforms, right? Did the light cone never change? Why? The speed of light is the same for all observers, independent of their relative motion. So that's what we're trying to do. And books do it right, but unfortunately do it confusingly. Because all of a sudden they will transition from having never talked about the Lorentz transform to all of a sudden dropping the Lorentz transform on you, expecting you to know instantly what all the symbols mean, and then boom, they start writing down all of their equations with Lorentz transforms, primes, and u's, and all kinds of stuff. So what I have done is I have come up with a different set of symbols. Maybe this is just adding confusion to the fire, but I am the kind of mind where if it's burning already, just throw more fuel on it, right? If it's a dumpster fire, just let's get it out and make it burn really fast. So what I have done is I've actually kind of rewritten this. So I'm going to do this slightly, it's the same math, I'm just using different symbols. I've noticed over the years that the Lorentz transform symbology just is really rough for the majority of students. Maybe you figured out right away, that's great, okay? But I had to do this when I went through all of this stuff, and it helped me a ton to be able to do it this way. So maybe it's just this is the way Mr. Balogh's brain works, okay? But we're going to define three velocities. And as long as you live by these definitions, you're going to be okay. There's going to be V1, V2, and V, okay? V1, okay, this is the speed of object 1 with respect to WRT, our observer. So again, the person on the planet saying object 1 is moving at 0.8 times the speed of light. V2 is the speed, you want to take any guesses? Of object, good, right? This makes sense, right? With respect to the observer, okay? So we would say V2 is, in this case, negative 0.9 C. Why would we have to say negative? It's moving the opposite direction, okay? V then, okay, is going to be the speed of object 2 relative to object 1. In the book, they will have the same definitions. They'll say speed of object relative to observer, but they'll use like u and u prime, sometimes u1 and u2. It just kind of gets, not the band, it gets kind of crazy, especially when you're not used to the language of the Lorentz transform. So this is why I fall back just on v's. V is velocity, right? And we'll just label them with subscripts and we'll be fine. We don't have to worry about primes or anything else. Okay, with those definitions out of the way, we can find out what V2 is with the following transform equation. I'm not going to prove these. I'm not going to derive them for you. You're just going to take them as gospel truth. Okay? So this is a result of applying the Lorentz transform to the problem of velocity addition. Okay? Regular Galilean transformation, classical, right? Don't have to worry about speed of light and time dilation, length contraction. Would not have the denominator, would just have the numerator. Okay? So that helps us find V2, but quite often what we're trying to find is the relative velocity between the two moving objects. And so what I've done for you, and what books tend not to do for you, is I've solved the thing in the box for V. It's going to be V1 minus V2 all over V1, V2 over C squared minus 1. So you're welcome. Did a bunch of algebra there for you. It's not hard, but it's a bit of a waste of time. Okay? If you have those two boxes and you have the definitions at the top, you should be able to safely navigate any relativistic velocity addition problem. You can find what speed the objects would see each other approaching at, or if you knew the speed that they're approaching at and then you knew the speed of just one of them, you could find the speed of the other respective observer. So let's do some examples. Right? Let's just apply what's on the screen right here. Unfortunately, I got to take it off the screen to be able to go to the next slide. So we're just try to remember, okay? V1, what's V1? Speed of object 1 according to who? The observer. What's V2? Object 2 with respect to the observer. And what's V? Good. Okay, and I'll bring the equations out as we do that. Yeah.
Is solving for V1 going to be the exact same way as solving for V2?
Yeah, we just gotta do the algebra correctly, but yes. Yeah. All right. So we're doing science fiction, right? Or science fact. So let's throw in a little science fiction, shall we? Okay. The USS Enterprise, Captain Picard, okay, approaches Earth, and the Imperial Klingon ship Bortas, which in Klingon means revenge. Is that okay? So get our nerd on here. Anybody know what the Bortas was? Familiar with it? No? No Star Trek Next Generation fans? This is the Klingon cruiser that Worf got stationed on. It's Gowron's flagship. And Worf got stationed to it when he left the Starfleet for 1.5 episodes. And finally came back. So yeah. Watch Star Trek Next Generation. It's available in 4K now. Oh, I just heard that all of the movies are now available in 4K. Paramount released all of the Star Trek movies, starting from number 1, all the way up through the J.J. Abrams verse in 4K. Don't watch Star Trek 1. Not unless you're really into Star Trek. It's very weird. Very true. Okay. Start at Star Trek 2. Don't miss Star Trek 4. Probably have to watch 3 in order to understand 4, but 4 is the better movie. Okay, where are we at? Okay. Set up 3 people, right? There's always 3 things. What are the 3 things? Enterprise, Bortas, and Earth, right? So again, what's the common observer here? It's Earth, right? And then you have the Enterprise And then you have the board toss. I can do my Star Wars or my Star Trek clip art. Okay. And so let's see. If we say that the Enterprise is going to the right, and we call the right positive, we'd say plus 0.6c. So what does that mean we have to write down for the board toss if it's moving the opposite direction? Yeah, you got to be careful with your signs here. Okay. All right, so in the language of what I just taught you, what's V1, what's V2, and what's V? What's V1? Pick one, Enterprise or board toss, it doesn't matter. Okay, we're just going to call it the Enterprise. So V1 is that. What's V2? It's the other object speed as measured by Earth, right? Remember, V1 and V2 are both measured by the same person. That make sense? Okay. All right. And they want to know, like Picard wants to know how fast the Klingon ship is approaching. Right? So we're going to use the equation that starts with V, because V is the relative speed that the two ships see each other at, right? V1 and V2 we know. We want to solve for V. And I told you that was V1 minus V2 all over V1 V2 over C squared minus 1. All right, so we dropped some numbers in here. V1, 0.6C minus a minus 0.7C all over 0.6 times a negative 0.7 minus 1. What happened to the C squared down there? It cancels out, doesn't it? Okay. All right, so when I do all that, I get negative 0.92C. Not, what would that be, 1.3C? Right, the classical version would be 1.3C, but we can't go faster than the speed of light. And the relativistic version corrects for that, and we get a 0.92. But there's a negative sign on it. So negative because of the math, but like, what does the negative sign mean? Remember, V is the speed that object 1 sees object 2 approaching at. What direction is object 2 going? To the left, right? Coming at. Picard seeing it come this way, right? Picard says my velocity is positive. Klingon ship has a negative, right? So usually we ask for like the magnitude of the velocity, right? Not the direction too much. But the direction is in there if you mind your positive and negative signs. It's important to get your positive and negative signs correct in this, okay? So we found what it is, and it's below the speed of light, and so we're all good. Let's do another example. Okay. Wolf 359, famously the site of the battle against the Balogh, first contact of Starfleet with the Balogh. Okay. It is a real star system. Okay. It is 7.8 light years from Earth. Okay. And so what I want you to do is in pairs or groups or something right now, figure out what the actors are and then figure out whether it's V1, V2, or V. Right? Try to set up this idea that there's like a third observer that's watching two things happen and see if you can't decide what V1, V2, and V are. I'll give you a couple minutes. Go.
So yeah, 0.09 is the speed, so that's how much, that's how they're averaging.
All right, how we doing? Yeah? It's hard, isn't it?
So is the observer in this case would be the enterprise?
Okay, right. So this is the question, right? Okay. Have you been able to identify the three actors? What are they? The Enterprise, probe, and then the starship that's at Wolf 359, right? Okay. So get those down in some sort of visual setup. Okay. So Enterprise. Lame Enterprise. There we go. Okay. Enterprise, right? Now, if we say the Enterprise is moving to the right and it fires a probe, is that probe in the same direction or opposite direction as its motion? Same, right? It's like the probe, which is going to be another one of my carrots, right? Okay, is moving along like that, right? And they're both headed towards Wolf 359. Okay? And I'm not going to draw the ship that's in orbit around 359. It's just they're sitting at 359, right? Okay. So they gave us, right, some speeds. So let's tackle the first speed, 0.9 c. Who's doing the measuring? Is it the Enterprise or is it Wolf 359? The answer is yes. Because if the Starship Enterprise sees Wolf 359 coming at them at 0.9 c, what is a ship at 359 going to see the Enterprise doing? Coming at them at exactly the same speed. So the 0.9 we could attach to the Starship Enterprise, right, as seen by Wolf 359. Okay? And vice versa. Well, I'm going to get to your question here in a second. Okay, we have another speed, 0.8 c. Now what's that the speed of? The probe according to who? Ah, okay. So here we get some very definite information. The Enterprise says that this probe is moving at 0.8 c, and why did I give it a positive sign? Same direction, right? Okay. Is that what Wolf 359 sees?
No.
No. Right? Because of relativity. Like, if this were classical Galileo, we'd say 1.7, wouldn't we? But that's not how it works. Okay? So the question now becomes, what the heck are these things? Right? What's V1, what's V2, what's V2? So, again, V1 and V2 are always speeds measured by a single person. Right? Somebody that's doing looking from somewhere. And Jeff's question is, well, do I make Wolf 359 the central observer, or do I make the Enterprise the observer? And the answer is it doesn't matter. If you're consistent with the signs that you choose, you'll get it right. Okay? I'm going to go ahead and choose Wolf 359 as my central observer. It's the one that it kind of intuitively people will reach for. They assume stars and planets don't know, right?
But the probe is being measured from the perspective.
Correct. So if we say Wolf 359, right, is the central observer, we would then, what would V1 then be? 0.9. Right? We've already established Wolf 359 and the Enterprise agree on the speed that they are traveling at, right? What would the 0.8 then be? It's measured by who? The Enterprise. and it's measured a speed of another object relative to itself. That's v. Not v2, because what's v2 going to be? The speed measured by Wolf 359. V1 and V2 are measured by the same person, right? So if we say somebody's on 359 and we're looking at the Enterprise, we say that's 0.9, then the probe has to be V2. But the 0.8 we were given was measured by the Enterprise from its frame of reference. And so that's V. V2, the probe's V2 is our unknown thing. We want to know how fast the probe is moving according to people standing on Wolf 359. Kathy, did you have a question?
No, I just got my definitions mixed up.
It's easy to do. Okay, definitions getting mixed up is easy to do. So you want to make sure that you nail that idea that V1 and V2 are measured by the same person. Right? Whatever person you want to make the central actor, just make sure you keep your definitions the same. I'm making my central actor Wolf 359, and since 0.8 was given by Picard on the Enterprise, I know that has to be V. Okay, so we're solving for V2. I gave you the equation for V2. It's V1 plus V all over 1 plus V1V over C squared. So that's going to be V1, we say positive 0.9C plus a positive 0.8C. I'm being very careful by like explicitly stating my signs here, right? I want to be able to go back and see if I messed up somewhere. Maybe I messed up in a sign. 1 plus 0.9 times 0.8. C's disappear. And I get positive 0.988C. What does the positive sign mean? Also moving to the right, right? We specified to the right as being the positive direction. And so we're not surprised that people will 359, they say the Enterprise is moving in positive 0.9, right? And everything lines up in the same direction, that we would get the same sign. But that's not surprising. 0.988, good answer because it's less than 1. Anything over 1, something gone horribly wrong. With either your math or the universe. Probably your math. Just as a guess. So, relativistic velocity addition is just a little taste of the Lorentz transformation. The Lorentz transform can get pretty hairy in a conceptual framework. Okay, mathematically, it's not too hard to kind of turn the crank. But it's really difficult to kind of line up what's prime, what's not. You got to be really careful about assigning your variables and to things like that. And it's true here. You got to be careful, but it's a little bit easier the way I've formulated it.
So you said it doesn't matter what we said, if we saw the sun moving towards, the star moving towards the thing. So that if we said that the star was moving towards the ship, would the V1 be negative like that?
Right. Yep. And you solve for V. And then the signs would all work themselves out. Yep. Physics is relative. And by that, we don't mean it's up to anyone's guess. We mean it very strictly obeys its own rules. Yeah. It's only confusing in the sense that you want to believe that there's an absolute frame of reference. And while there actually is, and we'll get to it on Monday, for special relativity there isn't. And we are only doing special relativity, right, for now. We'll do general relativity on Monday. Maybe a little bit today, but probably on Monday. Because it really depends on how long it takes me to get through this next part. Because we've done space, we've done time, which means that we've also done velocity, because velocity is space and time together, right? Now we got to do everything else, right? Mass, momentum, energy. Can't do accelerations yet, that's general relativity. We can do this, okay? let's jump in here. Momentum. What's momentum? Like classically, what was momentum?
It was like kinetic energy.
Mm-hmm. It's been a long time since 4A. Is that what you're talking about?
Masses.
Yeah, it's MV. I fried your brain. Now you're asking me to recall something from before relativity. You've altered my understanding of the universe, and you want me to go back? Sometimes you'll come to me and say, "Can we just go back to the easy stuff?" It was MV. Okay, and conceptually, it was kind of a quantity of motion. And the bigger the mass something had, the more motion it had, right? Even though the speeds might be the same between a car and a train, we'd say the train has more motion, right? Like there's going to be more of an impact when that train hits something versus a car, right? So momentum was this way of quantifying the motion of an object, okay? Again, without proof, because that takes a graduate degree, I'm just going to tell you that the relativistic momentum is gamma mv. Sometimes you see this is written as gamma mu. Okay, again, kind of being weird about U or V. V is the relative speed between frames. So if we're watching something go by, that's the relative speed. Let's just call it V. That's the relativistic momentum. We're gonna deal with this for the rest of the semester, but don't worry. I'll prepare your minds for when it comes back around. What's gamma?
1 over the square root.
Okay, 1 over the square root of 1 minus v squared over c, right? But more conceptually, it's a factor, right? It's a factor that depends on the relative speed measured between observers, isn't it? So if your relative speed is 0, your gamma factor is 1, right? And then what would the momentum of an object be? 0. If the relative speed, if you are standing there and a car has a relative speed of 0 with you, what's its momentum? 0. If you and the car are on a tow truck that's moving at 50 miles an hour, what do you measure the momentum of the car to be? 0. No, but the road, Mr. Beck. Relativity. You and the car not moving relative to each other. You can be moving at 50 miles an hour and you could bump into the car and you would not be hurt. Because the car is not going 50 miles an hour relative to you. Right? What is gamma operating on here? If v is the same v, the relative velocity, what's the only thing that's left? What's mass? It's like salt, right? It's good on chicken. Yeah. Mass changes with relative speed. Time changes, length changes, mass changes. And it changes like this. The relativistic mass of an object is gamma times m naught, where m naught is called the rest mass. The mass something has when it is not moving. This is the mass that you have always used in physics up till this moment. Even though all through 4A, the cars and the penguins and the goats and whatever it was that we had, llama was sliding down a hill, I got a goat, it was a goat, right? Even though they were moving at such slow speeds that the gamma factor was so close to 1 and it didn't matter. But now, it matters. And so the relativistic mass is something that we need to correct for. Where does mass show up in physics? In Newton's laws? In energy? In moment? Yes?
So is the relative mass what goes in?
So we could write, so if I was being symbolically careful, this would have been gamma m naught. Right? Or I could have written just mv, wink wink, it's the relative mass. Usually, when we're in relativity, we're very careful with m naught or the rest mass, sometimes m sub r, and being very explicit about it. But in general, in practice, if you see just m, chances are it's the rest mass all the time. And when you're doing relativity, you throw gammas into everywhere. Otherwise, it gets kind of confusing. What happens to the mass of an object the faster it goes? It increases. It increases by a factor of gamma. So for something that's moving at 0.95 times the speed of light, where your gamma factor is about 10, and it weighed a kilogram, or has a mass of a kilogram, how much is its mass now? This is not a trick. It's not an optical illusion. That object's mass is 10 kilograms. How do we know this? We do this all the time with electrons and protons in particle colliders. There's a particle collider in the basement of every hospital, major hospital, to make their radioactive isotopes. We'll get into all of this later. But they speed up electrons and protons up to very close to the speed of light and slam them into certain targets to produce radioactive isotopes that they then inject in people so they can put them in the MRI machines and see all their tissues. Okay, they're called radioactive tracers. Can't make those on the East Coast and ship them to the West Coast because the half-life is measured in minutes. So you got to make it, put it into the person, and get measuring right away. So in the basement of every major hospital, there's a device that can speed up electrons and protons to very close to the speed of light. We're talking like 0.9999 C for these things. And their mass changes. The mass of an electron, when it's moving 99.99% the speed of light, is more than that if that electron was at rest. Same goes for the protons. We measure this every day. It's part of your brain that wants to sit there and go, none of this is real, and live in a simulation or something. You're reaching for sanity because you want the lie that you have lived your entire existence to continue. That lie of the ground is solid or this way is positive. I have been fighting against those lies since day one. When you came to me all innocent and foreign, right? And you thought you knew how the universe worked. And this class was like nothing but one abuse session after another, me telling you how you were wrong, or your intuition was failing you, blah, 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 right? Okay? I don't do it because I enjoy it. I do enjoy teaching physics. It's true. That's the thing. That's the hard part. The bitter pill to swallow. When you go out and measure these things, they actually happen. See if I can't prove it to you. Let's answer a different question first, though. Why can't anything that has mass go the speed of light? And why is somebody cutting down trees? Afraid if we close the doors, can you know how to do it?
Based on the gamma factor, it would be 0 based on the speed of light. So, just mathematically.
No, you're close. You're really close. Go ahead and close the doors. We'll see if they quit here in a minute.
Because it would require infinite energy to push that.
Okay. If we take a mass and we push it to the speed of light, what's its mass become? Infinite. How much force do you need to accelerate infinite mass? An infinite amount of force. And an infinite amount of force applied over any distance is an infinite amount of work, which would require an infinite amount of energy. And how much energy does our universe have? A finite amount. Our universe does not have an infinite amount of energy. It has a finite amount of energy. There's a cap. It's the amount of energy there is in the universe. Energy is always conserved. Can't make it, can't destroy it, but it's not infinite. So why can't things that have mass move at the speed of light? Our universe does not allow for it. There isn't enough energy. So there's the answer to that question.
Does light have mass?
Ah, okay. So what's the one thing that does move at the speed of light? Light. Why does it move at the speed of light?
Because it's light.
Reverse the argument I just made.
Is everything else is that?
Because it has no mass. Massless things, pure energy, by definition, have to move at the speed of light. They can't move at any other speeds. Things with mass can all move at sublight speeds, but never attain light speed. Mass tells you how fast something can go.
Does that mean it doesn't need energy?
Need? Everything needs energy. I'm not sure I understand your question.
Well, because your argument was.
Let me see if I can't help you refine it just a little
If
bit.
it was an infinite mass, it would need an infinite amount of force, an amount of work, and an amount of energy to move. But if light doesn't have mass,
Then you don't need to work against it, because force can't be exerted against something that doesn't have mass, right? So all that argument kind of goes. So what does that mean about how fast light is going when it's created? Take a stick, burn it. Light comes off. How fast is it going? Did it speed up? Did it accelerate to get there? Instantaneously is moving at that speed because it doesn't have any other speed it can go. Anything without mass in our universe must move at the speed of light. Anything with mass is always stuck moving slower. Somewhere between 0 and very close to 1 C.
There's no other lives that will break this like quantum mechanics, right?
No.
I was gonna say something very simple, but now that I think about it, I know I'm working on it. I was gonna say that light has infinite acceleration.
Nope. Because to accelerate something requires mass and force to be applied to it.
What about photons? What is photons?
Yeah, what are photons? They're packets of light, they're chunks of light, they're particles of light. Okay, fine.
So it's massless.
Yeah. Photons don't have mass.
How does plants absorb it?
How do they absorb the energy? There's very specific frequencies and wavelengths associated with that packet of light. Now we're getting to quantum mechanics. We'll get there.
So if you slow down light, and then you take it out of the situation where it's slow, does it accelerate?
You can't do that.
slow it down.
You can't.
So you can slow it down. We've been doing that the entire time we were in optics. What does the index of refraction tell you? How much the light slows down when it encounters a material.
So the moment
The speed of a wave depends on what? The medium in which it is traveling. So light travels slower in water than it does in air. So what happens when it transitions from water into air or vice versa?
So then it just
It instantly changes its speed. But the one thing that doesn't change, that most of you missed on the exam, the frequency. That's going to be very important when we get to quantum mechanics. Anyway. Okay, go ahead.
Sorry.
No, it's
So,
good.
when it's changing speeds in the medium, is there any sort of change to its mass?
No. Light has no mass.
So you can't add mass to it?
No. As soon as you do, it has to move slower than the speed of light, and therefore it is not light.
So you can change its form?
No. Not yet. We'll get there.
What about light?
How are your brains? Yeah. I have nuked the bucket. It's just like, okay, it gets worse. Energy. What's energy? In physics 4a, we defined work as a force over a distance. Okay? You integrate and you go from some initial position, some final position, you get something, right? Okay? And another way to write force is to write it as a change in momentum in time. X initial, X final, right? But we now know that momentum is gamma mv. So what happens when you stick that in there? And now your v depends on x and t. How nice is this integral? Not nice at all. So I'm not going to show you any of that. I'm going to do an AMO step, which is a miracle occurs. Because Einstein took several pages to do it, and I don't want to do it. Einstein derived the kinetic energy of an object that is moving at relativistic speeds, meaning gamma is significant, right? Gamma is, there's more than like a 1% difference, right? So this kinetic energy, according to Albert Einstein, is gamma mc squared minus mc squared. I don't know what you think. MC squared. There it is. But we're not there yet. No, we're not there yet. Kinetic energy. Notice how there's a difference here, right? Kinetic energy is being expressed as a difference. In general, the total energy that something has is a combination of its kinetic and potential energies, where I'm using capital U as the symbol for potential energy because that's the standard one. So that means if we rearrange this to solve for kinetic energy, we get total energy minus potential energy, right? What's total energy according to Einstein? Can you see it? Kinetic energy is a difference between total energy and potential energy. So what's total energy according to Einstein?
Oh, yeah. Nothing?
I broke the computer. I broke your brains, and I broke the computer. Oh, this computer rebooted itself for some reason. Yeah, it is your fault. I'll put a ticket in. It's not your fault. But what's happened is
The power thing.
yeah, it's turned off and it's turned back on again. It'll be back in about 5 minutes. Okay, I'll keep going on the board.
Relativity is so confusing that you
Yeah.
have a break going on.
Yeah.
I don't know.
Don't worry, people on YouTube, I'll take pictures. Okay? So, the total energy is gamma mc squared, right? Coming from, remember Einstein said it was gamma mc squared minus mc squared. That's what he derived for the kinetic energy of something, right? And I said that, well, kinetic energy is expressed as a difference between the total energy and the potential energy. So the total energy has to be gamma mc squared, and that means the potential energy is what? mc squared. In other words, an energy that involves some sort of relative motion, the gamma is in here, right? The relative motion's applied. But over here, no relative motion. It's just math, right? So I know you're thinking, oh, well, but like, that's E equals mc squared, isn't it, Mr. Balogh? E equals mc squared isn't the whole story. It's way cooler. Way cooler. And I'm going to show you. This is what Einstein did. It took him several years and months, whatever, right? I'm going to do it in about 4 minutes. Not because I'm smarter, but because he did it first. Let's get rid of this for a second. We don't need that right now. Okay, what we are going to need, though, is momentum. Okay, gamma mv. I'm going to go ahead and I'm going to draw vector sign. I mean, we know they're vectors, but positive and negative. We'll just deal with that. It actually isn't that important. Oh, by the way, this came to be referred as to the rest mass. Or sorry, the rest energy. And so that's how it got the E equals mc squared terminology, right? It's the rest energy because it's the energy something has simply because it has mass. So in 1905, Albert Einstein was the first person to tell us what mass was. What is mass according to Albert Einstein? It's energy. What's energy? Mass. Didn't really help, but it was a step in the right direction. Two sides of the same coin. But the rest mass refers to, like the mass of my water bottle, right? Okay? If I could convert all the mass of my water bottle into pure energy, big if, okay? Then the amount of energy I would have would be enough to power the entire energy needs of the United States for 1 month. It's C squared. 300 million squared times the 800 grams of my container. Now, so why aren't we running America on water bottles?
We're not smart enough.
Because in Montana, they're saying they're going to get rid of all electric cars because they need to save the fossil fuel industry.
Be the same place that's trying to take away teaching theories in school.
Yes. So, Montana, Florida. We can't do that because when we try, it's called a nuclear bomb. Take a mass, convert it into energy, you get a bomb. Okay? We can also do it in the nuclear reactor. That's a small one. Actually, it can never blow up. For reasons we'll get to at the end of the semester. But we're not very good at that conversion. At best, we are about 5% efficient at that conversion. Hard to do. So, that's where that came from. But let's get to this. Okay, so I'm going to do some mathematical trickery here. This is what Einstein did. Okay, let's square both sides of this. Okay, that's going to get us gamma squared, and then I'm going to write this as mc squared quantity squared for reasons that will become apparent in just a little bit. And then I am going to divide both sides by this mc squared thing, so I can just get gamma squared on one side. And then I'm going to take the momentum, gamma mv. And I'm going to do the same thing. I'm going to square both sides of it. You're like, well, why are we making it more complicated, Mr. Beal? Well, Einstein did, so we'll just trust that he knew what he was doing. Okay. Let's divide both sides by m squared. Here's gamma squared v squared. And then I'm going to multiply by 1. Now, when physicists say they're going to be multiplying by 1, you know something crazy is about to happen. Why did I multiply by 1? Or how did I multiply by 1? What's c squared over c squared? 1. If I do one side, I do the other, I can cancel it out, I still get the same thing, right? So that's physics talk for I multiply by 1. It's not literally 1, but I can do whatever I want as long as I do it to both sides. Okay, now we are going to take the difference between these two equations. We do e squared over mc squared minus p squared over m squared c squared. And if I subtract the two left-hand sides of these two equations, what do I have to do to the right-hand side? Take their difference, right? Difference of the left, difference of the right. So that would be gamma squared minus gamma squared v squared over c squared. Can I factor a gamma squared out of this? What's gamma squared? It's 1 over the square root, but the square root goes away, doesn't it? And what do I have? 1 minus v squared over c squared? That's gamma squared. And then I have a 1 minus v squared over c squared on the top. What's on the right-hand side of this equation? 1. This is a very complicated way of writing the number 1. You don't get the joke yet. You will in quantum mechanics. Okay. Now, I'm going to clean this up a little bit. Okay. And I'm going to skip a few math steps here so that we can get to the punchline. Okay. This is going to end up being e squared equals mc squared squared plus pc quantity. Do you guys want to see those steps? No. Good. Okay, that was the correct answer. Plus pc squared. So basically, I've got kind of some common denominatory stuff going on over here. And if we tweak it just a little bit, we'll end up with. So we move this over to the 1 side. There's 1 plus all this stuff. And then we can factor out some n's and some c squareds as long as we pick up an extra factor of c on the momentum term. Okay? So it's just a little tiny bit of algebra. And finally, I can solve for the energy. So this is Albert Einstein's formulation for the total energy of any object. So relativistic energy. This is it. It is the square root of mc squared squared plus pc squared. This is the equation that ended up in the second paper on special relativity. The first paper was all concept and ideas and thought experiments. The second paper was the mathematical formalism of relativity, and this was Albert Einstein's punchline. That is the equation that should be on every t-shirt. That's the equation that should be in every comic strip or book or whatever, or written on the chalkboards on the NOVA documentaries behind the physicist's head. Not E equals mc squared. This one! The complete one! The actual one! So why does E equals mc squared get all the credit? It's not the truth. It's a specific instance of this energy. What is the momentum if an object isn't moving? So, when an object is at rest, okay, it will then have an energy of E equals the square root of mc squared squared plus 0, take square root, and you end up with E equals mc squared.
If it is at rest, then how come it's moving at the speed of light?
It's not moving at the speed of light. mc squared has no velocity term in it. C is just a constant. It's the speed of light. It's this term right here that has the momentum in it. This is the motion. This is the kinetic energy term. Here's your potential energy term. Well, maybe it's coming back. Okay, so everything I've told you, though, is not the interesting part. It's not the melt your brain part. You thought your brain was melted? Get ready. Hold on to your desk. The interesting question is not what happens if it's not moving. The interesting question is, what happens when it has no mass? Let me let you stew on that for just a second. I'm going to make sure I record this for posterity. Okay, so there we go. This should be, this will be in the PDF, right? So because of technical difficulties, we went from here to here, okay? But what we've got in the end is that the real deal is this, right? So if the momentum is 0, in other words, the relative velocity is 0, then E equals mc squared, hooray. But if the mass is 0, so what are we talking about now? Light. If what we're talking about is light, how much energy does it have? Your brain has given up on math because it wants to believe a lie. It's not 0. The mass is 0. According to Albert Einstein, then the energy is PC. Okay? But what?
Yeah, mass. There's a momentum of mass involved.
Is it momentum supposed to have mass in it?
Yeah.
Can something that has no mass have momentum?
Oh. Well, if it's light.
What? 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 Does light have momentum? Does something that is inherently massless have momentum? This particular light bulb has a vacuum in it. They pulled all of the air out, okay? And inside they put a funny sort of array of white and black triangle diamonds, okay? And it's sitting on the head of a pin, basically, so there's very little friction here, okay? So there's no way for any energy to get through this bulb, okay, in the form of, say, molecules bouncing around in there. There's a vacuum in there, right? They've sucked all of the material out, okay? That means that this thing can only move if we kind of like mechanically shake it, right? I can kind of get it to spin if I give it some impulse and mechanically shake it, okay? So I caused it to move right there, but if I don't do anything, it is eventually going to slow down. So there's a little bit of friction in this system, right? It's not like I have a perfectly superconducting anything, okay? It's just glass resting on metal, that kind of thing, right? But as you can see, it's coming to a stop. I have here a light bulb. I just made something go the speed of light, right? Does light have momentum? What's the answer? Yes. That light bulb is 25 watts. This light bulb is 650 watts. Okay. Okay. Are we ready? Here it goes. Do you see how much faster it's going? Okay?
The light bulb has a bigger, it's using more wattage than most computers.
Yeah. So, does light have momentum?
Yeah.
Yeah, it does. We've done this in orbit around our planet. It's called a solar sail. It's been tested by NASA. It works. You can get propulsion from the photons that are coming from the sun, bouncing off the reflecting surfaces of the solar sail. Satellites have to correct for the momentum they are hit by from the sun, from the light that bounces off of their surfaces in order to stabilize their orbit. In fact, it was the way that the Kepler Space Telescope was able to keep collecting data even after 3 out of 4 of its gyroscopes failed. They were able to use what NASA called the momentum pressure from the sun to basically angle the telescope into the wind and use that last gyroscope to kind of keep it pointing in the right direction. This is very real, very physical, and everything you thought you knew about how the universe works is probably wrong. I'll see you on Monday for general relativity.